Basic planar processes. Here we have silicon wafer preparation, epitaxial growth, oxidation, photolithography, diffusion, ion implantation, isolation technique, metallization, assembly, processing and packaging. Silicon wafer preparation. Here we have 5 different processes: crystal growth and doping, ingot trimming and grinding, ingot slicing, wafer polishing and etching, and wafer cleaning. The starting material for crystal growth is highly purified polycrystalline silicon. The Chokrovsky crystal growth process is the most often used for producing single crystal silicon ingots. The polycrystalline silicon, together with an appropriate amount of dopant, is put in a quartz crucible and is then placed in a furnace. The material is then heated to a temperature in excess of the silicon melting point of 1420 degrees centigrade. A small single crystal rod of silicon is called a seed crystal, is then dipped into the silicon melt and slowly pulled out. As the seed crystal is pulled out of the melt, it brings with it a solidified mass of silicon with the same crystalline structure as that of seed crystal. During the crystal pulling process, the seed crystal and the crucible are rotated in opposite directions in order to produce ingots of circular cross section. The ingot is then sliced using a stainless steel saw blade with the industrial diamonds embedded into the inner diameter cutting edge. This produces circular wafers or slices. Epitaxial growth, the basic chemical reaction used for epitaxial growth of pure silicon is the hydrogen reduction of silicon tetrachloride, SiC4 plus 2H2, leads to at 1200 degrees centigrade Si plus 4HCl. Most epitaxial films are specific impurity concentration are required. This is accomplished by introducing phosphine for the N-type and biborane for the P-type doping into the silicon tetrachloride hydrogen gas stream. The process is carried out in a reaction chamber consisting of a long crystal quartz tube encircled by a radio frequency induction coil. The silicon wafers are placed on a rectangular graphite rod called a boat. This boat is then placed in the reaction chamber where graphite is heated inductively to a temperature of 1200 degrees centigrade. The various gases required for the growth of desired epitaxial layers are introduced into the system through a control console. Oxidation: the silicon wafers are stacked up in a quartz boat and then inserted into quartz furnace tube. The silicon wafers are raised to a high temperature in the range of 950 to 1115 degrees centigrade and at the same time exposed to a gas containing oxygen or H2O or both. This oxidation process is called a thermal oxidation. The thickness of the film is governed by time, temperature and the moisture content. The thickness of oxide layer is usually in the order of 0.02 to 2 micrometer. Photolithography. Photolithography involves two processes, namely making of photographic mask and photo etching. Photographic mask is the preparation of initial artwork and secondly its reduction. This initial layout is then decomposed into several mask layers, each corresponding to a process step in the fabrication schedule. For example, a mask for base diffusion, another for collector diffusion, another for metallization and so on. Photo etching is used for the removal of SiO2 from the desired regions so that the desired impurities can be diffused. The wafer is coated with a film of photoresistive emulsion, Kodak photoresist. The thickness of the film is in the range of 5,000 to 10,000 angstrom. The various steps for photo etching: the mask negative of the desired pattern is placed over the photoresist coated wafer as shown. This is now exposed to ultraviolet light so that KPR becomes polymerized beneath the transparent regions of the mask. The mask is then removed and the wafer is developed using a chemical trichloroethylene. It dissolves the unexposed and unpolymerized regions on the photoresist and leaves the pattern as shown. The chip is immersed in the etching solution of hydrofluoric acid, which removes the SiO2 from the areas which are not protected by the KPR as shown. After diffusion of impurities, the photoresist is removed. The chemical solvent, that is hot sulfuric acid, and mechanical abrasion. Diffusion, a quartz board containing about 20 cleaned wafers is pushed into the hot zone with the temperature maintained at about 1000 degrees centigrade. Compounds such as boron oxide, boron chloride are used for boron, and phosphorus pentoxide and phosphorus oxychloride are used as sources of phosphorus. A carrier gas such as dry oxygen or nitrogen is normally used for sweeping the impurity to the high temperature zone. Ion implantation. Ion implantation, this is to introduce impurities into a silicon wafer. In this process, silicon wafers are placed in a vacuum chamber and are scanned by a beam of high energy dopant ions as shown. These ions are accelerated by energies between 20 kilovolt to 250 kilovolt. The ions strike the silicon wafers. They penetrate small distance into the wafer. Isolation technique. We have two techniques: p-n junction isolation and dielectric isolation. p-n junction isolation. In this isolation technique, P plus impurities are selectively diffused into the n-type epitaxial layer so as to reach P substrate. This produces islands surrounded by P-type modes. Dielectric isolation, here a layer of solid dielectrics such as silicon dioxide or ruby completely surrounds each component, thereby producing isolation, both electrical and physical. Possible to fabricate both the PNP and the NPN transistor within the same silicon substrate, but it is more expensive, mostly used for fabricating professional grade ICs required for specialized applications, namely aerospace and military. Metallization. The purpose of this process is to produce a thin metal film layer that will serve to make interconnections of the various components on the chip. Aluminum is usually used for the metallization of most ICs. The process takes place in a vacuum evaporation chamber. The pressure in the chamber is reduced to the range of about 10 power minus 6 to 10 power minus 7 torr. The material to be evaporated is placed in a resistance heated tungsten coil or basket. A very high power density electron beam is focused at the surface of the material to be evaporated. This heats up the material to a very high temperature and it starts vaporizing. These vapors travel in straight line paths. The evaporated molecules hit the substrate and condense there to form a thin film coating. After the thin film metallization is done, the film is patterned to produce required interconnections by photolithographic process, and aluminum is etched away from the unwanted places by using etchants like phosphoric acid. Assembly, processing and packaging. Finally, each of the wafer processed contains several hundred chips, each being a complete circuit. So these chips must be separated and individually packaged. A common method called scribing and cleaving used for separation makes use of a diamond tipped tool to cut lines into the surface of the wafer along the rectangular grid separating the individual chips. Each chip is then mounted on a ceramic wafer and attached to a suitable package. There are three different package configurations available, namely metal can package, ceramic flat package, dual inline. It may be ceramic or plastic type package. So this diagram shows the T05, that is called a metal can package, mainly used for transistor fabrication. And this second diagram shows 14 lead version of the flat package. Thank you.